Hello everyone, welcome back to Knock Knock Yaar Education. Myself Alka Singh Chauhan, and today we are with a new topic, linear transformation. So I hope all of you are doing good. So let's get started with this topic, linear transformation. But usse pehle let me announce one thing, that we will be doing this topic in detail, and we will try to cover the whole portion that is being mentioned in the syllabus of IIT-JAM. So linear transformation, and after that we will cover eigenvalue, eigenvector also, and few topics which are left we will try to cover them in the next lectures. So let's see today how much we can cover in this linear transformation. So let's get started, and first we will try to understand what is the linear transformation. So as all of you know that this is the part of the linear algebra where they have mentioned the topic linear transformation. But what do we mean by linear transformation? So let T from V to W be a mapping. Okay, so this is going to be a mapping for us, and this is a special kind of mapping. Why? Because usually we study the mapping from a non-empty set to a non-empty set, but here the sets which are written like V and W, they are special kind of sets such that this V and W, let V and W be vector spaces over the field F. Vector spaces over the field F. So this is an important thing, that this V and W, they should be vector spaces, but make sure you remember one thing, that both the vector spaces are on the same field F. Then this mapping T is said to be a linear transformation. I will write down linear transformation by LD. If and only if, what should be the condition? That for all u and v vector which belongs to V, and for all alpha comma beta vector which belongs to field F, what should be the condition? T of alpha u plus beta v must be equals to alpha times T of u plus beta times T of v. If this condition gets satisfied, then we will say that this mapping T is a linear transformation from the vector space V to the vector space W. So I hope now all of you are very clear with the definition of the linear transformation, that linear transformation is nothing but this is just a mapping from one vector space to the another vector space over the same field F, such that for every vector u and v in the vector space V, and for every scalar alpha beta in field F, T of alpha u plus beta v must be equals to alpha times T of u plus beta times T of v. Any of the mapping which satisfies this condition for every vector u v in the vector space V and scalar alpha beta in the field F, then that mapping becomes the linear transformation. But this is just the definition. We will see few examples on it today, so that you people are more clear with the linear transformation. So in this session we will be talking only about the examples, and I will also tell you few tricks to check whether this is a linear transformation or not. Then from the next lecture we will be covering our theory portion also, like null spaces, range spaces. So we'll cover this topic in very detail. So let's go through some examples. Suppose I have given you a mapping from R2 to R2, like T of x comma y is equals to x comma 0. Now you can see that x comma y is a member of R2. So we have defined a mapping, that a member of R2 is being mapped to the member of R2, but it is mapped in such a way that its second component becomes 0 and the first component remains same. Fine. So first we will check that whether this is a well-defined map or not. So this is a well-defined map. Why? Because R2 over R is a vector space, R2 over R is also a vector space, and this is mapping a member of R2 to the member of R2 itself. Fine. So now we will check whether this mapping is a linear transformation or not. So for this, what we have to do is that we will simply apply the definition to see whether this forms a linear transformation or not. So for all u which I am considering at x1 y1 and v which I am considering as x2 y2 which belongs to R2, and for all alpha beta which belongs to field of real number, I am just checking this condition which I am marking as 1. So what I am doing is that t of alpha u plus beta v I am evaluating, that is t of alpha times x1 comma y1 plus beta times you have x2 comma y2, which is going to be t times, this is alpha x1 plus beta x2 comma alpha y1 plus beta y2. Fine. So according to the mapping, the first component is being mapped as it is and the second component is being mapped to 0. So this is going to be alpha x1 plus beta x2 comma 0. So we have written it like this. Now the next step, we can do it in different ways. Like here I have written alpha u plus beta v, that become equal to alpha x1 plus beta x2 comma 0. So we can do it like this also, alpha x1 comma 0 plus this is our beta x2 comma 0. Now you see that t of u, that is our t of x1 comma y1, this is being equal to x1 comma 0, and t of v, that is our t of x2 comma y2, this is being mapped to x2 comma 0. So we will directly use this. I can write it down, alpha times x1 comma 0 plus this is beta times t of x2 comma 0, sorry, this is our x2 comma 0. So now I know that x1 comma 0 is equal to t of x1 y1 and x2 comma 0 is equal to t of x2 y2. So this is going to be t of x1 y1 plus this is going to be t of x2 y2. So now this is what, alpha times t of u plus beta times t of v. So this is how we check that condition 1 is satisfied over here. So t is a linear transformation. Otherwise the other way to do is that you consider it equal to LHS. So this expression become equal to this, and you find out RHS also. That was your alpha times t of u plus your beta times t of v. So this is going to be t of x1 comma y1 plus this is going to be your beta times t of x2 comma y2. Now this is going to be your x1 comma 0, this is going to be your x2 comma 0. Now this is going to be alpha x1 comma 0 plus this is your beta x2 comma 0. Now you add, this is alpha x1 plus beta x2 comma 0. So this is the same expression that we are getting on LHS. So both the LHS and RHS are equal. It implies condition 1 is fulfilled. So that is why this given t is a linear transformation. That's how we check whether the given mapping is a linear transformation or not. So let's do one more example for it. Suppose I am giving you like t of, we have R2 to R2. We will do on many more vector spaces, but for now let's do it on R2 only. So t of, we have x comma y is equal to x plus y comma y. So how is this mapping is defined? That your first component is being mapped to the sum of both the components and the second component is mapped as it is. That's how the mapping is defined. So let's check whether this is a linear transformation or not. So we will go by LHS, that is t of alpha u plus beta v, where I am considering u equals to x1 comma y1 and your v equals to x2 comma y2 from R2, that is your vector space v, and for all alpha beta which belongs to field F. So this is going to be t of, once you are going to find out alpha u plus beta v as we did in our previous question, this is going to be alpha x1 plus beta x2 comma this is alpha y1 plus beta y2. So how is this being mapped? The first component we are getting after mapping is the sum of both the components, so that is alpha y1 plus beta y2, and the second component is mapped as it is, so we just mapped it like this. Now we will find out the RHS part, that is alpha times t of u plus beta times t of v, that is equals to alpha times t of x1 comma y1 plus beta times t of x2 comma y2. Now this x1 y1 is being mapped to the x1 plus y1 comma y1, and this is being mapped to the x2 plus y2 comma y2. So what here we got is alpha x1 plus alpha y1 comma alpha y1 plus beta x2 plus beta y2 comma beta y2. Now you add both the tuples, you will get alpha x1 plus alpha y1 plus beta x2 plus beta y2. Then you got alpha y1 plus beta y2. Now you see one thing, because R2 is a vector space over the field of real numbers, so you might have learned about the properties of the vector space, that vector addition is being satisfied. So see one thing, these this vector and this is also a vector, they belong to R2 because R2 is a vector space, so they satisfy the property of commutativity with the respect to the vector addition. So what I can write it down, beta x2, then I can write it down alpha y1 plus beta y2, and that is equal to alpha y1 plus beta y2. So now see, this LHS become equal to the RHS, that is for all UV in R2 and for all alpha beta in field F, T of alpha u plus beta v becomes equals to what? Alpha times T of u plus beta times T of v. So that is why this mapping T also becomes what? A linear transformation. So this was our second example to understand whether the given mapping is a linear transformation or not. Now let's proceed to few things which are quite important for us to check whether this mapping forms a linear transformation or not. So I'm going to tell you one important thing, so you can note it down keeping a note on your notebook. The first point here we have is, if T is a linear transformation, if T from V to W, which is a mapping, is a linear transformation, then what happens is that T of 0 must be mapped to 0. Fine, where this V is coming from where? From the vector space V, and this is coming from where? From the vector space W. And you can very easily understand this, because we have written T of alpha u plus beta v equals to alpha times T of u plus beta times T of v. For what? For all uv in the vector space V and for all alpha beta in field F. So if this is true for all alpha beta, we can choose alpha equal to beta equal to 0. Now you see T of 0 becomes equal to 0. So if T is a linear transformation, T of 0 will definitely go to 0. One more important thing, what? T of minus u is going to be equal to minus times T of u for all u in the vector space V. This is also very simple to understand. How? We choose alpha equal to what? Minus 1 and beta equal to 0, because T is a linear transformation, it is already given. So for all alpha beta this is going to be true. So I am considering alpha equal to minus 1 and beta equal to 0. Now you see, minus 1 times u plus 0 times v is equal to minus 1 times T of u plus 0 times T of v. What it become? T of minus u equal to minus times T of u. So it means if we are checking any mapping as a linear transformation, you need to check these two conditions first. Now the conclusion about all this, what I told you, is that suppose I gave you a mapping from V to W and I asked you a question whether this forms a linear transformation or not. So before going through your definition, you check one thing. And what is that one thing? You check T of 0 is being mapped to 0 or not. If yes, then what you will do? You have to check, because you cannot say whether this forms a linear transformation or not. But if this is not satisfied, then T is not a linear transformation. Why? Because अगर वो linear transformation होता तो T of 0 तो 0 पे जाता ही ना, by definition हो रहा है वो तो. बट अगर वो नहीं हो रहा है इसका मतलब T नहीं है. लेकिन अगर हो जाता है, then we will not say anything whether this T is a linear transformation or not. I'll give you examples, we will check it. And suppose if this condition satisfied, so you can go one more step. What? You check whether T of minus u is equal to minus times T of u or not for all u belonging to V. If this condition holds, then you need to check further. Now what do you mean by further? You will proceed by definition. Definition means for all uv in the vector space V and for all alpha beta in field F, T of alpha u plus beta V must be equal to alpha times T of u plus beta times T of V. And if this does not hold, आप डायरेक्ट बोल सकते हो that T is not a linear transformation. So these two conditions are really very important because they will just give an idea कि how we are saying that whether this forms a linear transformation or not. So now I'll give you few examples to verify all these points which I have told you just now. So let's get started with few examples. So the problem number 1 that we are going to do here is that suppose I gave you T from R2 to R2 and I defined it like T of x comma y is equal to, suppose I gave you this is x plus 1 comma y. Okay, so first I will tell you where the property fails or whether this is a linear transformation or not. Then I'll give you the parts which I have discussed just now. So for all u which is our x1 comma y1 type and for all v which is our x2 comma y2 type which are belonging to R2 and for all alpha beta which belongs to field F. Okay, what we are doing here is that we are doing here T. And one more important thing I would like to mention here. What is that? Just now I have told you one thing, that this property should be hold. Okay, this where I have marked it as 1, this should be hold. So in most of the books you can see one more thing. What is that? Instead of this direct thing, that is T of alpha u plus beta v equals to alpha times T of u plus beta times T of v, they have given it in 2 steps. Whether you satisfy this or what you can do, T of u plus v must be equals to T of u plus T of v and T of alpha u must be equals to alpha times T of u. So this is your one step test to check whether the given mapping is a linear transformation or not, and this is your 2-step test to check whether the given mapping is a linear transformation or not. Here we are checking vector addition and scalar multiplication in 2 steps, and here we are checking in the similar steps. Okay, so like either you can do it this way or that way, both are equivalent. So suppose if I talk about this question, so let's see, we are doing it with the 2-step, we can do it with 1 step also. So T of u plus v I am evaluating, that is equal to what? T of your x1 plus x2 comma y1 plus y2, because that is going to be equal to u plus v. Where it is being going to be mapped? According to this, the first component plus 1, that is x1 plus x2 plus 1, then we have y1 plus y2, second component remains as it is. Now if we evaluate T of u plus T of v, that is our RHS part. So this is your T of x1 comma y1 plus your T of x2 comma y2. Now this x1 y1 is mapped to where? X1 plus 1 comma y1 plus x2 plus 1 comma y2. Now what it will be? X1 plus x2 plus 2 we got, and here we are getting y1 plus y2. Now you observe the things. Here we are getting x1 plus x2 plus 1 and here we are getting x1 plus x2 plus 2. That means T of u plus v is not equals to T of u plus T of v for all uv in R2. That means this T is not a linear transformation. Now see, this much of work we have done. Fine, and let's come to the point which I told you just now. If T is a linear transformation, then the 0 vector of R2 will be mapped to the 0 vector only. What I did, I just checked T of 0, 0. Where it is going to be? 0 plus 1 comma 0. Fine. So what it will be? This is going to be equal to 1 comma 0. Now you see that your 0, 0 vector is not being mapped to 0, 0. So T of 0, 0 is not equal to 0, 0. That is why directly we can say that T is not a linear transformation. Instead of solving all this, in exam you can just do these kind of simple things to check whether this is a LT or not. Okay. So that's what I have explained you in this point, कि if t of 0 is equal to 0 does not hold, then t is not a LT. Now I'll give you one more example on this so that you can clearly understand. T of R2 is from R2 to R2, and I am giving this t of x comma y is equal to, suppose this is 0 comma sine y. Fine. It means first component is being mapped to 0 and second component is mapped to the sine of its angle. Fine. So whether we have to check whether this is a LT or not. So see one thing. Here if we evaluate t of 0 0, this is going to be 0 comma sine of 0, which is obviously 0 0. So don't say from here that t is a LT or t is a linear transformation. Don't say it from here. I have already told you, if this satisfied, check. You cannot say whether this is a linear transformation or not. If you're directly going to say from here that t is a LT, obviously you are going to lose your marks. Okay. So now in this case, t may or may not be, t may or may not be a LT. We will check it further. Or you can apply that condition also, like t of minus u. Fine. So from there also you will check that this condition is being satisfied. As such, there is no problem. So we will go through the definition now. What we are going to do here is that for all u comma v, for all u comma v which belongs to R2, I am doing it in two step only, where your u is x1 y1 and your v is x2 y2. Fine. So this t of x u plus v is going to be what? It is going to be t of x1 plus x2 comma y1 plus y2. What it will be? First component is being mapped to 0 and the second sine of its angle. So this became equal to this. Now if we evaluate t of u plus t of v, see, this is going to be t of x1 comma y1 plus it is going to be t of x2 comma y2. So what it is going to be? The first component is being mapped to 0. So we will map it 0, and this is going to be sine of y1 plus this is going to be 0 comma sine of y2. Now you add both the tuples. 0 plus 0 is 0, and this is your sine of y1 plus sine of y2. Now you see one thing, that in this t of u plus v, we are getting second component as this, and in this t of u plus t of v, we are getting second component as this. And we know that for all y1 y2 which belong to R, it is always not possible that sine of y1 plus y2 becomes equal to sine of y1 plus sine of y2. This does not hold for all y1 y2. That is why this t is not a linear transformation. So I just wanted to explain you this point, that if t of 0 is equal to 0 holds, you will not say anything. Even if this holds, the given mapping may or may not be linear transformation. But if it does not hold, you can very clearly say, like in this example, that t is not a linear transformation. Okay. So let's discuss the second part also. Like this is saying t of minus u is equal to minus times t of u. Suppose I gave you one example which is like this, t of R2 to R2. I am giving you t of x comma y is equals to, we have here mod x comma y. Fine. So we need to check whether this forms a linear transformation or not. We can see t of 0 0 is being mapped to mod 0 comma 0, which is nothing but 0 0. So obviously we cannot say from here anything, so we will check it. So what I did, I consider u as x1 y1 and I am considering v as x2 y2. Fine. And now I am checking for t of u plus v, that is going to be equal to x1 plus x2 comma y1 plus y2. So this is going to be mapped to where? This is going to be mapped to mod of x1 plus x2 comma y1 plus y2. Now if we evaluate t of u plus t of v, what we are getting? T of x1 comma y1 plus t of x2 comma y2. Now you observe one thing, this is going to be your mod of x1 comma y1. This is your mod of x1 comma y1 and this is your mod of x2 comma y2. See one thing, this is going to be mod of x1 plus mod of x2. This is going to be y1 plus y2. see one thing, that for all x1 x2 in R, this cannot be hold. For all x1 x2 in R, mod of x1 plus x2 is not equal to mod of x1 plus mod of x2. I mean, there exists some x1 x2 for this condition holds, but this does not hold for every x1 x2 in R. So it implies what? That t of u plus v is not equals to t of u plus t of v. That is why this given t is not a linear transformation. Okay, so whenever mod function comes in front of you or trigonometric functions comes in front of you, you can directly say whether this forms a LT or not by looking at these conditions. Now you see one thing. If I evaluate t of minus u, which is t of minus of x comma minus of y, where u I am considering as x comma y, it is going to be equal to like this. So this is mod x comma minus y. And if I evaluate minus times t of u, this is going to be t of x comma y, which is minus sign mod x comma y, which is minus of mod x comma minus of y. Now you look at both these values. T of minus u is mod x comma minus y, and minus times t of u is minus mod x minus y. So that is why I was saying if this condition fails, t is not going to be a linear transformation, as we can see in this case. So instead of checking all this, you just check both these conditions initially. If these are satisfied, then you proceed with the definitions. Otherwise, there is no need to proceed by these definitions. You just check these conditions. If these are satisfied, go for the definition part. If these are not satisfied, directly you can see that the given mapping is not a linear transformation. No need to go for all these kind of definitions. So this is how our work becomes easier when we go by these kind of things. So let's do a few more examples. We'll cover 2-3 more examples, and then we can end up with this session, and in our next session we'll start with the theory part a little bit more. So let's talk about few example kind of linear transformations. So the very first that we are going to study is our identity transformation. What is this? We will understand, because this is going to be very helpful for us in our further lectures. So identity linear transformation is what? Suppose we have a mapping from a vector space V. The important thing over here is that to a vector space V. Okay, so here we cannot have any other vector space. This is a mapping from V to V, and this is defined like I of u is going to be equals to u only for all V, for all the vectors V u in the vector space V. That's how the mapping is defined. It means every member is being mapped to itself. So if you will see it like here, so आप इसको ऐसे दे सकते हो. Suppose this is our V and suppose this is our V. Okay, so every member, and this is a mapping I. So every member which is here, it is being mapped to here. Suppose this is your x1, this is mapped to x2. Suppose this is your x2, this is being mapped to x2. So like this, every member is being mapped to itself. So this kind of mapping we have been given, and now we will check whether this forms a linear transformation or not. Obviously I have given it the name identity transformation, it will form, but we will see how it forms. So for all u comma v which belongs to V, what I did, I of u plus v I evaluated. So as you know, every member is being mapped to itself. Since u and v belong to V and V is a vector space, so u plus v will also belong to V, and any member of V maps to itself, it means it will go here. And one more thing, since your u is in vector space V, your v is in vector space V, so I of u is going to be equal to u, and your I of v is going to be equal to V only. So now you can substitute it like this, u is equal to I of u and v is equal to I of v. So our first condition is being what? Is being satisfied. Now we come to our second condition, what? That is for all alpha in field F and for all u in the vector space V. I of alpha u we are checking. You know that V is a vector space. So for every vector u in the vector space V and for every scalar alpha in the field F, alpha u belongs to where? It belongs to V only. So it will be mapped to itself. This is going to be like this, and again I have written, since u belong to V, so I of u is going to be equal to V only, so we can write it down I of u. Again the condition fulfills. That is why this is called as the identity transformation. Like if we define a mapping from the vector space V to the vector space itself, where every member is being mapped to itself, this is a linear transformation, and such transformation we named it as identity transformation. Okay, so this is going to be very helpful for us, because in further lectures we will find out its null space, its range space. So you just learn it, that there is a kind of linear transformation which is identity, which is defined as this. Fine. Let's go to another very important transformation, that is our null transformation. And नाम से ही पता लग रहा होगा आपको, जैसे हम मैप्स के बारे में पढ़ते थे, ज़ीरो फंक्शन, नल फंक्शंस, ऐसा कुछ है. सो क्या हो रहा है यहाँ पे, लेट्स सी. वी हैव डिफाइंड ज़ीरो ट्रांसफॉर्मेशन एज फ्रॉम V to W, where this of u equals to this for all u belonging to vector space V. So I am going to just show you like this. Suppose this is our V and this is our W, fine, and we have defined, we just have represented it like this. You can represent it by T, I, whatever symbol you want, but we generally define it like this. So obviously every member is being mapped to 0. So suppose here we have one member, here we have another member, here we have another member. All these members are just being mapped to the single vector, that is u vector inside the W. Fine. So such kind of mapping is also called as zero mapping or null mapping. So we will just check whether this forms linear transformation or not. So for all u comma V which belongs to V, what is happening? U plus V will also belong to V. Why it is the case? Because V is a vector space, we all know. That's how we have defined the mapping. So 0 of u plus V is going to be where? It is going to be 0 only. Why I am saying this? Because every member of V goes to 0, and u plus V is a member of vector space V only. I can write it down this 0 as 0 plus 0 by using the additive identity property of the vector space W, and this is, we can write it down like this. But there is a difference in both these steps. I'll explain you in detail. Here the 0 that I have mentioned, both these zeros are coming from where? Suppose let me write it down like this. Okay, this I have written it like this. So 0 of u plus V is equal to 0. I wrote it down like this. I can write it down like 0 of u plus this is 0 of V. So what I want to explain you is that in this mapping, this is belonging to W. So don't get confused, because 0 of 0 also goes to 0. Why? Because this is how it is. Every member of V is being mapped to W. So 0 vector is also in V, so that is also being mapped to W. But this is from V and this is from W. So don't get confused in these kind of notation. It is very obvious, you can understand. Fine. So because using the additive identity property of the vector space W, I can write it down 0 as the 0 plus 0. And since your u and V are belonging from where? Vector space V. So 0 of u is going to be equal to 0 and 0 of V is going to be obviously equal to 0. So we proved the first property. Now the second one is, for all alpha belonging to field F, 0 of alpha u, it is going to be equal to 0. Why? Because for all u belonging to V, alpha u belongs to V. Why? Because your V is a vector space. So this is going to be like this, and I can write it down what? You can alpha times 0 of u, you can find out, that is also alpha times 0, which is 0. Both this becomes equal to 0. It implies what? That your zero transformation or null transformation is a linear transformation. So आप बस इतना याद कर सकते हो, ये मैपिंग, कि that's how we have defined it. Okay. सो आज की क्लास के लिए बस हम इतने ही एग्जाम्पल्स रखेंगे. इन आर नेक्स्ट क्लास वी विल डू फ्यू मोर एग्जाम्पल्स अलॉन्ग विथ सम theory portion. But before that I am just leaving you with a very important point. आप लोग comment box में मुझे बताओगे कि actually क्या है. So the point is that if T is a linear transformation, it implies that T is a function, and you know very well now the difference between the function and linear transformation. And if T is a function, then your T is a linear transformation. Basically इतना सब कुछ लिखने से अच्छा है अगर मैं ऐसा लिख दूँ आपके पास T is a linear transformation if and only if T is a function. It is going to be correct or not, this statement is correct or not. आप या तो इसका काउंटर देना मुझे कमेंट बॉक्स में, या आप अगर सही है तो इसका प्रूफ एक छोटा सा लिख के मुझे प्रोवाइड कर सकते हो. एंड लेट्स सी हाउ मेनी ऑफ यू कैन गेट द करेक्ट आंसर फॉर दिस क्वेश्चन. सो आई विल वेट फॉर ऑल ऑफ योर्स आंसर्स इन द कमेंट बॉक्स and I'll see how many of you reply to it. So wait for the next lecture. Very soon I will give you the next lecture on linear transformations as well, and we will try to cover the whole linear algebra on this platform only. So that's it for today's class. Thank you so much.